These piezometers are a special type of single tube manometer. So we've got a group of piezometers that we've attached to a pipe here. And if this valve is closed and this reservoir is full of water to this depth H, then initially all of these tubes which are connected to the pipe, they'll all have the same water level in them, and it'll all be up here at the same level as the reservoir, because the top of each of these piezometer tubes is open to atmospheric pressure. So if there's no difference in pressure between this location and this location, then there must be no difference in height through the water around to that other tube. Now that's if everything is sitting static. If we open this valve and we get a whole lot of water flowing out, then we no longer have a static situation down here in the pipe. And if the levels are changing in these tubes, we no longer have a static situation in the tubes. But once they come to a steady position with their level, we will have a static situation in the tube. So although the pressure is dropping along the pipe due to friction, we can still use fluid statics to calculate the pressure differences between 1 and 2 based on the heights of these fluids and the fact that they're both at atmospheric pressure at the top. So let's look at what's going to happen. This is at atmospheric pressure. This is at atmospheric pressure. The pressure at 1 is rho g times h, less a little bit for the friction there. The pressure at 2 will be lower still because there's been more friction, so there's been a pressure drop. So the result is that this liquid level is going to drop down. The pressure at 3 and so on. And finally, when we get to 4, we'll be very close to atmospheric pressure again, so there'll only be a very low level in this piezometer tube. And in fact, if we drew our energy grade line from here in a straight line down to here, we'd see the elevations in the tubes changing approximately like this, allowing us to figure out the pressure at 4, P4, is equal to P ATM plus rho H2O times G times that distance in there, H4. And likewise, for example, P2 equal to PATM, that's the pressure in this tube, and because it's full of air, we can neglect the changes due to air, times this height H2 to get us down to location 2, so plus the density of water times G times H2. And that allows us to get a visual representation of how the pressure is dropping as we go along this pipe. And that's very useful to understand the different elements that we might put in here that could produce that pressure drop. For instance, if we had a different diameter of pipe, or we had some additional fittings in there or something like that, we can, if we actually built piezometer tubes, we could see the changing height in those tubes. Or if we use them as an exercise for thinking about pressure drops, we can visualize what's going on by thinking about the energy grade line as it drops down along that line as we go along the pipe. If you understand your fluid statics well, to recognize that these dropping levels in these piezometer tubes correspond to drops in pressure as we go along the pipe, then when we get to Module 6, where we're looking at the friction losses in pipes, you'll be well placed to relate this information back to what it means in terms of a drop along the piping system.